All right, class, we're going to get started. A couple of announcements before we begin. This morning, homework 2 was available on Canvas. Some of you may have already seen it. Homework 2 involves some amount of work about exploring linear classifiers. And then there's a couple of theory questions where you're proving things. And there are experiments where you'll implement the perceptron algorithm and several of its variants on a data set involving where the task is to distinguish 2 digits, 4 and 9, I think. This homework, for reasons that are different from the previous one, this homework will take time. Hopefully by now you're comfortable with the code, or at least you've seen what the kind of code that we are expecting, or at least you've written some code and submitted it. So that pipeline is probably familiar, but this time around, the theory part might take time. And also the implementation, if you've never done this sort of stuff, it could take time. So I encourage you to get started soon. I also encourage you to use Piazza and office hours. Another suggestion is you're welcome to use libraries like NumPy for vector addition and stuff. But of course, you're not allowed to use machine learning libraries like Torch and such things, which you won't be able to get to run on the autograder anyway. NumPy and SciPy and such things are available, I believe. So take a look at the requirements.txt file that's in the code that we've provided to get a sense of what libraries are available. Any questions about homework 2? Yes.
So it's already released?
Yes, it is. It's not.
It's on Grayscope, but not on Canvas.
It's on. It's on Grayscope, but not on Canvas. Okay, we will have to. We will make it available on Canvas after the class, or maybe even during the class. Okay, during the class. It's on Grayscope. Good catch. Other questions? Yes.
Theory, you can also explain, the description, right? Is there any description of pages?
Yes. I was arguing for no more than 10 pages. My TA suggested 15, so we are going with 15. It's mentioned in the homework document that, and this time for your experiments, you'll also have to write something in the report. You'll have to show some plots, and you'll have to write some description on what how your design choices that you used. So all of that together should be no more than 15 pages. And I don't think this will take 15 pages. I think you can do the homework within 10. Other questions? There's also going to be an announcement about the project. On Thursday, there'll be some updates on that this week and also the next week. There's nothing to say here. Just watch out for some information on this. Okay, other things that you want to talk about? Logistics, questions? Okay, so we're going to now go back to where we were with the perceptron algorithm. Just a reminder, the perceptron algorithm that we saw before was this very simple mistake-driven learning algorithm. I'll pull up the algorithm so that you can see it again. This is the entirety of the algorithm. So this is the mistake-driven algorithm. At least the original version that we encountered was purely in the online setting, where there's a stream of examples that are coming along. And for each example that comes along, x, y, first, the algorithm makes a prediction here. And the prediction, this is a linear classifier. So the model here is just a set of weights. So the prediction is simply take the dot product of the weights of the features So WT transpose XI, and look at the sign of that number, and if that's basically the output, if it's a +1 or a -1. And if the prediction and the ground truth disagree, then you have the perceptron update, which is WT plus 1 is WT plus R is called the learning rate, times Y and Y times X. So you take for a positive example, the new weights are old weights plus Xi, but scaled with a learning rate R. And for negative example, the new weights are W is W, the old weights, minus Xi, minus the example. This is the entirety of the perceptron update rule. And in the last lecture, we saw what this was, and we also looked at a couple of intuitive explanations for what's going on, why these are reasonable, why this is a reasonable update. And the short answer is, if the algorithm makes a mistake on a positive example, after the update is done, the dot product of W and X increases because you're essentially adding X to the W, so the weights look more like that example, so the dot product increases. So if it made a mistake, that means that the old weights were negative and you're adding something positive to it, so you're making it less negative. And similarly, for the negative examples, or on a negative example, if it makes a mistake, you are taking away Xi, which means the score W transpose X decreases after the update. And we also looked at a geometric intuition, which is basically the hyperplane rotating every time the update happens. There's also some shifting because of the bias term. We posted a video on Canvas showing this update on a randomly generated data set in 2 dimensions. I encourage you to take a look at that. So this was pretty much all we saw in the last lecture. Any questions about the perceptron update? You're going to be implementing not exactly this, but a sort of a grown-up version of this, if you will, for your homework. And we'll talk about those variants today. One person is nodding. I'm assuming that means everyone's nodding. So let's assume that everyone's nodding. Feel free to ask questions. So what we're going to do now is look at some of the variants of this idea. The perceptron algorithm itself is rather old. It's from 1957 or 58. So there's been enough time for many, many variants to have been invented. The first variant that we'll encounter is something that addresses a more practical need. The original perceptron algorithm was designed in this online setting. We assume an infinite stream of examples that keep coming in. And for every example, you make an update. In practice, we don't have an infinite stream of examples. We have a finite data set. So how do we simulate an unending stream of examples using only a finite data set? The answer to this gives us what I'm going to call the standard perceptron. This is the when people say they use the perceptron algorithm, that's what they usually implement. And then after that, I'll talk about a rather important idea for the perceptron algorithm called averaging, which invariably leads to improved performance. And then after that, I'll introduce a variant of the perceptron called the margin perceptron, which may not always be better, but it's like foreshadowing an important idea that we'll encounter later on. So let's get started. The standard perceptron looks exactly like the original perceptron, except in fact, this block here is basically the perceptron algorithm. So let me first go through the thing that I just shaded. You iterate through examples, x, y, and if there is if the current set of weights makes a mistake on the example xi, yi, then you make an update. Now, notice that this is how I define a mistake. If y w transpose x is less than or equal to 0. Because if y w transpose x is less than or equal to 0, that means y and w transpose x have opposite signs. Y is positive and w transpose x is negative. That's a mistake because we want them to have the same sign. If y is negative and w transpose x is positive, that's also a mistake. And those are the only kinds of mistakes. A slight bit of a technicality here. Notice that I have less than or equal to 0 here. And the less than equals is important because we're initializing the weights with 0. So in the very first step, the very first example that comes in, you'll have equality equal to 0, so it will trigger an update. If you did not have a less than equal to there, you will never ever get an update. That's a bug that I have seen often in students' code, just letting you know. Okay, so that's just the perceptron algorithm. You initialize your weights to 0 and then you iterate over the data once. But we have only a finite data set. So in the standard setting, we have a finite data set D, which consists of some number of examples, but clearly finite. And each example, of course, is a feature vector X, which is a D-dimensional feature vector that's paired with a label, which can be either -1 or 1. Now, I would like to simulate an infinite data set or an infinite stream of examples using only a finite number of finite data set. One way of doing that is rather boring, but it works, which is you have a finite data set, you just put a for loop around it. You just keep iterating over the same data again and again. You're going to see the same examples again and again, but it's never ending. Or it ends when you run out of patience or something like that. So the standard algorithm, the way it proceeds, is you initialize your weights to something. In this case, it's 0, but we'll eventually, later in the semester, we'll see that it doesn't really matter what you initialize your weights to. And learning proceeds in epochs. An epoch is basically one entire pass through the training data. So learning proceeds in epochs, and within each epoch, you perform the perceptron update by iterating over the examples one at a time. So pick an example. If your current weights make a mistake on that example, you have W is W plus R Y X. It's the standard perceptron update. There's this one extra step in the middle which says shuffle the data. Every time you enter an epoch, you shuffle the data and then iterate through the examples. There's a technical reason for that. Basically, it has to do with the fact that you don't want your learner to, in some sense, learn something about the order of the examples in which the examples are presented, and you want it to be robust to that. That's the weak intuition I'm giving you right now. Later on, when we talk about stochastic gradient descent, you'll see that actually it turns out the randomness matters. For now, let's just say that if you do not shuffle the data, there's a good chance that the weight will not be as good as it could have been. And you do this for T epochs. You basically, for every epoch, what you do is first you shuffle the examples and then iterate over this shuffled data, pick an example. If the current weights make a mistake, apply the perceptron update, do this capital T number of times. At the end, you return the weights. This is the learning algorithm. And then once learning is done, you can take this weights that you have and make predictions on new examples. And the prediction process is exactly the same. Prediction is simply the sign of W transpose X. I mean, it's the same, it's a linear classifier, so you do the same thing that you do with all linear classifiers. Any questions here? Yes.
Just to clarify, this is a finite training set?
Yes, yes. You have a finite training set, which is what you had, for example, in your first homework, that's what you have in your second homework, that's what we have in life. Yep. Yes. R is the learning rate. I have not told you exactly how to set R. For now, let's just say that R is a small number between 0 to 1. And think of it as the step size. Or think of it as how much does each example affect the weight. It's the impact of any example on the weights. And as R increases, your learner will basically your model will can change quite a bit on any one example. In this case, it seems like R is the constant. And in practice, turns out that we want to not keep R as a constant, we want to change R. And as the number of epochs increases, you want to keep reducing the R so that the algorithm converges. But for now, let's not worry about that. There is R is for now a hyperparameter. It's just another, like your decision trees had a hyperparameter, right? The depth. Here we have a hyperparameter, which is the step size, R, but there's another hyperparameter, which is capital T. How many epochs should you run this for? Maybe you run this for 100,000 epochs and your learner will memorize the data set. Maybe you run this only for one epoch and the learner has not really had a chance to learn. So there's a sweet spot that you pick, that you need to find. And how do you find a good value for the number of epochs? You use another held out set. In your homework, we've asked you to use a validation set to find a good number of epochs, and the homework describes how you do that. But for now, let's just say it's another hyperparameter. As our learning algorithms get more and more complex, you will see that we will collect a lot of hyperparameters along the way. In your homework, we've actually told you which variant of perceptron has what hyperparameters and what values you should explore for those. And this is going to make this is the reason why it can take a while for your code to run, because you're going to try out a whole bunch of hyperparameters. Any questions about this particular variant of the perceptron, which I'm calling the standard algorithm? Yeah.
So is that pretty much the same as like if y prime is equal to 1?
The inequality there. So the question is this inequality exactly the same as is y prime not equal to y? It is. Because think about it this way, y prime in the previous version of the previous slide that I showed is nothing but the sine of W transpose X. This can either be +1 or -1. If it's +1, that means W transpose X is positive, and -1 means W transpose X is negative. Y times W transpose X is simply asking, do these two numbers have the same sign? If it is negative, that means they have opposite signs. If it's positive, they have the same sign. Yes.
I still don't understand why we use epoch, like why are we running through, like passing through the entire.
Why are we going through this data multiple times? So I'll give you the answer that I gave before. I'll repeat it, but I'll give you another version also. The answer I gave before is that the original perceptron algorithm was defined for an infinite stream of examples. We do not have an infinite set of examples. We only have a finite number of examples. So by going through the same data twice, you're pretending that you have 2x the number of examples. If you go through it 3 times, you're pretending you have 3x the number of examples. That's one version of the answer. In theory, you can do that forever and you'll have an infinite number of examples. Just so happens they're the same examples that show up again and again. But it's a way to simulate the infinite set using a finite set. That's one answer. Another answer is the following. Suppose you have an example, let's say xi comma yi, and your current weights make a mistake on it. And when you make a mistake on it, let's say you make an update. And when the update happens, the weights change. And let's say your update is aggressive and it changes the weight so much that the current example is fixed. But by doing that, maybe you have destroyed the signal that you learned from another example that came before. So you want to revisit that. So you want to revisit all the examples enough number of times so that you stabilize. This idea of stability can be made more. So the third answer for that is this idea of stability can be made more concrete by viewing this algorithm from the lens of optimization, which we will do as early as next week, actually. Not this algorithm, but we'll see another algorithm from an optimizer. And there, the standard sort of an optimizer does exactly this, has this behavior. Learning goes in epochs and we just iterate multiple times, and that leads to a more stable solution. Yes. How do I know it will converge? Now, that's a good question. So the question is, how do I know this will ever get to the same set of weights? There are two answers for that. If the learning rate R is fixed, there's a theorem. Let's say it's not this algorithm, but the original perceptron, one with the infinite number of inputs, is guaranteed to converge. We'll see that theorem later today. Another answer to that is if R is decaying, then this actually simulates a gradient optimizer. And it turns out that this problem that it's optimizing has some nice properties. We'll come to that when we talk about loss minimization. But that's a good question. How do you know it converges? Just because I show you an algorithm doesn't mean that, just because I show you some pseudocode and say this is an algorithm, doesn't mean it's an algorithm. Maybe I'm lying. Other questions? Okay, so now let's look at another variant of the perceptron. Now this is an interesting one. This is the version that I'm going to talk about right now is an impractical variant. And then I'll talk about a practical version of that. In the standard perceptron, in the original perceptron algorithm, also the standard version of the perceptron algorithm, we keep making updates to weights, right? You make a mistake. Let's visualize this. So you start with some weights W0. And then you encounter a bunch of examples. And maybe at some point, this W0 makes a mistake and it gets to W1. And then W1 survives a bunch of examples without making a mistake. And then you get to W2. Maybe W2 survives for a very short time, and W3, and W4 survives a very long time, and you get W4. Actually, you know what? Let me draw this slightly differently. W4 survives a very long time, you get W4, and then there's only one more example, and you get W5. And maybe that's where learning stops. You've decided that that's when you've run out of patience and you've stopped the learning there. The standard perceptron algorithm, what does it do? It says the final weights are W5. Every time you make a mistake, you update the weights, and after all the updates are done, you return the final weights. That's what we had here also, right? You return the final weights. But notice that something interesting is happening here. It looks like, if you think about these weights, the vector W1 survived many, many examples. Maybe W0 survives 10, W1 survives 1,000, W2 survives 5, W3 survives 10,000, and this survives only one example. When I say survives, what I mean is after seeing 10,000 examples for W3, without making a mistake, it sees an example where a mistake happened. Now, is the situation clear? So we have a sequence of weights, and every time there's a mistake, we update it. We are counting how many times has this weight survived before it made a mistake. Now, in any version of the algorithm that we saw so far, we will return W5. But look, the weight vector. What did I do here? Let's get rid of W. We return W4. There's only one example that it survived, and then you're done and you return the final weight. So W4 has survived one example. W3 has survived 10,000 examples, and yet you return W4. That means that the algorithm thinks W4 is better than W3, but is it really better? It's just an accident that example that made W3 make a mistake. And so let's call this example here Xi, Xj, Xk, XL. There are four mistakes that are made, right? That example XL shows up and forced W3 to update itself. But had it shown up earlier, maybe you'd have hit W3 sometime before, and it survived so much longer. Maybe W3 is a better example, a better weight vector. Because in this data set, if you think about it, how many examples do you have? We have 10 plus 5, 10 plus 1,000 plus 5 plus 10,000. So it is 1, 1, 0, 1, 6. These many examples. Out of 11,016 examples, the weight vector W3 survived 10,000 of them. If you have to pick one of these 5 vectors to be the best one, you would have probably chosen W3, because W3 makes only 1,000, has gotten 10,000 examples right. Does this make sense? So the question then is, maybe the thing to do is we should not be returning W4, the final weights. we should somehow bring in W3 and have it be the final output, because it has survived the longest. But that's also not right, because if you bring W3, then that means that an example like Excel is always going to make a mistake. So the voted perceptron is an interesting idea. What it says is the final output of this algorithm is not a single weight vector, but it's a set of all the weight vectors that have been encountered so far. So in this case, the final output will be the set W0, W1, W2, W3, and W4. So you get 5 weight vectors that get returned. And at the end, when a new example comes in, you ask all these vectors to make a prediction. You get 5 labels. Which label do you pick? Which label would you pick? The majority, how? You have 5 labels. Let's say 3 of them are plus and 2 of them are minus. Which one would you pick? Plus. Now let me tell you that the 3 pluses are from, I'll write it here. This is a plus, this is a minus, this is a plus, this is a minus, and this is a plus. Would you change your answer? What would you change it to?
Minus, because W3 has like 10,000 examples.
And also W1, which has 1,000, right? So what you're doing is you're giving these weight vectors votes. You're saying each weight vector gets votes, but each weight vector does not get the same number of votes. The number of votes the weight vector gets is the number of examples it survived. So W1 gets 1,000 votes, W2 gets only 5 votes, W3 gets 10,000 votes, and the final weight vector is the label that has the maximum number of votes. Because the ones that survived longest during training are more robust, and they should, the intuition here is they get more votes. Any questions? Yes.
One weight vector that has like way more votes than the other ones. Won't you end up just kind of following that?
In this case, yeah. I mean, in this situation, you basically just follow W3, right? In this case, that's obviously the case. In practice, you won't get such an uneven distribution. In practice, what you might get is you might get tens of thousands of weight vectors along the way, each one with a small number of votes. And what I just said should prompt a question. You get tens of thousands of weight vectors, each one of them gets a small number of votes. Imagine implementing this. How would that work? You're going to memorize every weight vector that you encountered during training and keep an array of counts for each one. In practice, this is a highly impractical algorithm. In practice, I don't want you to implement this, because if you do implement it, you will very quickly run out of memory. So this is like a theoretical idea of voting, of voted classifiers, which comes actually, it turns out it comes with very strong theoretical guarantees about the generalization of the model. The voted classifier tends to can be provably generalizes better, but in practice, this is horrible to implement because you're going to remember every weight vector. To put this in context, while it's not exactly the same situation, imagine that you were training. You can apply this voting idea for any classifier, right? Any model. It does not have to be a linear classifier. It could be very, very complicated models. So large language models are also models. You could apply the voting idea there, and there you have millions of updates. So you have millions of sets of parameters, and each set of parameter has about a few billion numbers, possibly tens or hundreds of billions of numbers, each of them, and millions of those such things. So we are going to run out of memory and any sort of compute before to do. So this idea is theoretically sound, but practically infeasible. So there's a compromise. A practical version of this is rather than remembering all the weights, you just maintain a running average of the weight vectors that you've seen so far. Whether the weight vector gets updated or not, you update the running average. And then the final weight vector that's returned is actually the running average and not any of the in-between weight vectors. And it turns out this, on one hand, does not have any theoretical guarantees, but practically this works pretty well. And it's actually very, very efficient to implement. I'll show you a slightly different version of this or a way to implement this slightly differently. It's just two extra bits to your original perceptron algorithm, and this is called the averaged perceptron. The same setting as before, we have a data set with a set of labeled examples, where examples are vectors paired with labels. You initialize your weight vector to 0, and you also initialize your running average, I'm calling it A, to 0, the 0 vector. And you go through the same motions. The learning proceeds in epochs. In each epoch, you first shuffle the data, and then you iterate over each training example. And then if there's a mistake, you make an update to the weights. And then irrespective of whether you make an update to the weights or not, you add the weights to the average. So this is basically a running total. The vector A gets gets updated irrespective of whether there's an update to the weights or not. That means weight vectors that survive longer contribute more to that A, to the running total. And finally, I just return the running total. Really, if I want the average, I should be dividing by some number, but I don't care because it's only the sign that matters, not the magnitude. Because prediction is the sign of A transpose X. In practice, when people say they implemented the perceptron algorithm, they usually mean they implemented the average perceptron algorithm, because this tends to always do better. Always is a strong word. This tends to almost always do better. Any questions about this? You will be implementing the average perceptron in your homework. Yes. Yes. You initialize the A, you update the A, and in the end, you return the A. That's a vector. Yes. It's the same. You're adding W to A, so it must be the same shape as W. A common bug that people have in their code with the average perceptron is this step is inside the if. So the bug is that you update the A only when there's a mistake. A should be updated irrespective of whether there's a mistake or not. There's a question on Zoom. In step 2, do we use the running average? For this part, we do not use the running average. For checking if there's a mistake or not, we use the weights. And that's another common bug. We use the weight vector to check if there's a mistake. We update the weights if there's a mistake, and then we add the weights to the average in every epoch. Sorry, for every example in every epoch. Other questions?
So even if there's no update on the.
Exactly right. You update A even if there is no update on W. Turns out that there is a sort of a somewhat simple programming trick that you can use to keep something that looks like a running average that only gets updated when you update a W, and then you compute the value of A outside. It's basically just because think about it, if you add A to W to A, and you have not changed the W, you can increment a counter. You can say that this weight gets added these many times, and there's a way to kind of update this. This trick has been invented multiple times independently. I will leave it as an exercise for you to try to invent that trick. If not, it's okay because this one works. But the most important point here is if you're using Perceptron, If you want to use the perceptron algorithm, I would recommend use the average perceptron. Averaging tends to help always. Averaging is an idea that also is not unique to perceptron. You can apply this idea for other models also. In practice, we don't see that too often because of the extra cost of maintaining two things now rather than one. In practice, we don't see that often, but in theory, you can apply this for any model where you are doing these sorts of incremental changes to the model parameters. Questions? If not, let's go to a third variant of the perceptron algorithm. This one's called the margin perceptron. So the idea here, or the intuition here, is that with the perceptron, we make updates when YW transpose X is less than or equal to 0. What does it mean to make a mistake when YW transpose X is less than or equal to 0 with respect from the geometric point of view? So you have a hyperplane, or a line, let's say, and if it's not quite exactly right what I'm going to say now, but let's say that the weight vector is a unit vector. That means W transpose X is really the distance of the line from the plane. And if YW transpose X is, so let's say this is X, and this is your W. If W transpose X is, in this case, positive and Y is negative, that means you are, the point should have been a negative, labeled negative, which means it should have been in this part of the hyperplane, but it's not, so it gets updated. But let's say, instead of being this far away, let's say the point was somewhere here. This is your X. It's on the correct side of the hyperplane. It's a negative example. It's on the negative side of the hyperplane. It's on the correct side, but it's very, very close to the hyperplane. Maybe you want to update the weights there also because it's too close for comfort. You want to introduce something like a margin of safety. One way of testing for that is, rather than checking that YW transpose X is less than 0, 0 is just a threshold here, you have another hyperparameter. If YW transpose X is less than some number eta, eta is a positive number. It's even if YW transpose X is positive, in this case, if this is a negative example, it's a negative example, so W transpose X would be negative, Y is also negative, so Y times W transpose X is a positive number for this example here. Y times W transpose X is a positive number, so technically speaking, there's no mistake. But it's a very small positive number, so let's fix it. So you have this threshold eta that says, if it is less than eta, I'm going to count it as a mistake even then. And you make an update when YW transpose X is less than eta. Eta is called the margin hyperparameter. You have another hyperparameter. So let's just count the number of hyperparameters we have. We have the learning rate, we have the number of epochs, and now we have the margin. Right? Questions? You'll be implementing the margin perceptron also in your homework. I think grad students will also implement another variant of perceptron, which is called the aggressive update. We've described it in the homework, but the intuition there is, after making a mistake on an example, you make an update, you automatically discover a step size R for each example that forces the model to get that, fix that one mistake. You take such a large step or such a small step that this example gets fixed. And you do that. This is an aggressive update. So maybe that point was a noisy point and you should not have fixed it, but you do that anyway. And so the aggressive perceptron need not always do better, but it has some interesting properties. You'll not be evaluating the properties, you'll just be implementing it and working with that. Questions? If there are no questions, we're going to now move to another topic or another point of discussion about the perceptron algorithm, which is the perceptron mistake bound. We have seen the perceptron algorithm. We've seen the variants of the perceptron algorithm. And now we're going to look at a certain property of this algorithm, which makes it a certain rather interesting property of this algorithm. Remember, we were talking about mistake-bound algorithms, and I showed you this halving algorithm that makes only a finite number of mistakes and so on. Or not just finite, I mean, the number of mistakes it makes is polynomial in the dimensionality. Turns out the perceptron algorithm, the original perceptron algorithm without the multiple epochs version, the original perceptron is a mistake-bound algorithm. And there are a couple of theorems that are at play here, and I'll first state them informally, and then I'll state one of them a little more formally. There's something called the convergence theorem. The convergence theorem essentially says, if there are a set of weights that are consistent with the data, in other words, there is a certain linear classifier. We don't have access to it, but there is an oracle linear classifier that perfectly classifies every example. In other words, this is a linearly separable concept. If the concept is linearly separable, then the perceptron algorithm will converge. It's guaranteed to converge. The other theorem is called the cycling theorem that says if the data is not linearly separable, then the original perceptron will cycle through a set of weights. We won't be looking at the cycling theorem in more detail. We'll look at the convergence theorem in a fair amount of detail right now. But from the learnability point of view, of course, the perceptron algorithm can only learn things that the underlying hypothesis class can represent. If the perceptron algorithm is learning a linear classifier, then the best case scenario is it can learn linear classifiers. It cannot learn things that are not linearly separable. The classic example for something that is not linearly separable is the XOR function, or more generally, the parity function. And there was an influential book, I think I mentioned this last week. There was an influential book from 1969 called Perceptrons that showed how the perceptron algorithm cannot learn these sorts of things. And it turns out XOR is not something that, it's not one of these made up situations that only occur in theory. There are certain natural properties that are naturally parity. You want an even number of legs for people. If you're detecting people in photographs, you'd like an even number of legs at most. You want an even number of eyes. Symmetries can naturally be framed as parity or something like that. So these are properties that occur in nature. These are concepts that occur in nature that cannot be learned by the perceptron algorithm, and that led to a bit of a dampening of the hype of the perceptron family of algorithms in the 70s. But the history aside, I want to spend a bit of time talking about the perceptron learnability theorem. The perceptron learnability theorem, just to remind you, says if a certain concept is linearly separable, then the perceptron algorithm will learn the concept. To formalize this notion, I need to introduce formally the idea of a margin. Margin is an important concept. We will look at margin with perceptron. It shows up in the statement of the theorem. And then we'll also look at margin when we come to SVMs later, support vector machines, when we come to that. But the simple idea here, it's actually a rather simple idea. Suppose you have a data set like this thing here. You have pluses and minuses. And let's say the data set is linearly separable. And you have some hyperplane, a line in this case, that separates the data. The margin of the data set is simply the distance of the nearest data point to that hyperplane. So every point is put on the correct side by this hyperplane. Negative points are on this side and positive points are on this side. And every point has a certain distance from the hyperplane. Which means that we have a finite number of points. That means there must be some point that's the closest. The distance of the closest point is called the margin. It's the margin of the data set with respect to this particular hyperplane. Any questions? Yes.
How is this distance typically measured? Just standard like
Euclidean.
distance?
Yeah. Yeah. You could make it more complicated if you want, but let's keep things simple because I'm going to make it complicated in other ways. So this, we have a data set and a particular hyperplane. Now, this data set is linearly separable, right? Obviously, it's linearly separable because I just drew a line between the pluses and the minuses. But this is not the only line that separates the data. I could have another line like this that also separates the data that says this side is plus. Now, this particular, let's call this line, the first line was 1, the second line is 2. Line number 2 has its own margin, right? Can someone tell me just by point and show or just somehow which point contributes to the margin? What is the closest one? Yes?
It's one of the red negative points in the.
This one here.
Yeah.
Yeah. So it's the distance of the closest point to the hyperplane. So line number 2 has a smaller margin than line number 1. I can have another line that looks something like this. Let's call this line 3. And 3 has maybe a larger margin than both 1 and 2. I've not drawn it well enough. So maybe 3 has a larger margin than both 1 and 2 in this case. So some hyperplanes have a larger margin. Some hyperplanes have a smaller margin. That means there must be some hyperplane that has the largest margin. So I can have something like this. And that's the distance, the margin of that particular hyperplane is called the margin of the data. The margin of the hyperplane is simply the maximum, sorry, the margin of a data set is simply the maximum margin that's possible among all possible separators. Assuming, of course, that the data set is linearly separable. We use the Greek letter gamma to represent the margin. Questions? I want you to kind of internalize this intuition because later on, not right now, but later on, we will be formalizing this and working with this concept of margin in a fair amount of detail. And the minute you start formalizing this, I have found the first people, when people see margins for the first time, when they see it being formalized, they get confused. And there's a reason for that. I don't want to confuse you with that yet, but I want you to internalize this intuition. The intuition is very simple. The intuition is that if your data set is linearly separable, then for every linear separator, there is some point that is closest to it. So the distance of the closest point to the data set is the margin of the data set with respect to that particular separator. Every separator has its own margin. And that means we can find a certain separator that has the largest margin. And that means that, and that allows us to define the margin of the data set. The margin of the data set is simply the margin, the largest margin that's possible among all possible hyperplanes that separate the data. For now, I'm going to use this margin, the intuition of a margin, to state the perceptron mistake bound. But one more piece of intuition with respect to the margin. Now imagine you have two data sets. There's one data set where all the pluses and minuses are very close to each other. And you have another data set where all the pluses and minuses are very far from each other. And let's say that we are not playing tricks with the camera by zooming in and out. Let's say that the camera is fixed. So there's some points, one data set that looks like this. The pluses and the minuses are very close to each other. Another one that looks like this. All the pluses and the minuses are far from each other. at the same scale. I'll move the, oh, I just realized that a little bit of the top is not visible. Okay, so you have that. Now, let's call this data set D1 and this data set is D2. Which one has the higher margin?
D2.
D2, because there is some separator that can, both of them are linearly separable. But for D2, there's a good gap between the pluses and the minuses. So in some sense, a data set that has a larger margin is quote unquote easier to learn. There's a bigger gap between the pluses and the minuses. So even if you randomly, here's a very bad learning algorithm. My learning algorithm looks like this. I'm going to take the data set and randomly throw a hyperplane at it and hope it separates it. I can keep doing that. I can keep doing that till I find something that separates it. You have a better chance of winning with D2 than with D1 because there's a bigger gap. So you might just get lucky more. You're more likely to get lucky. So D2 is an easier data set than D1. Larger margins means easier learnability. And any mistake bound that we have, any sort of convergence guarantee that we have, we hope reflects this intuition that a more difficult data set should take more effort to learn. We'll see that's what happens. So without further ado, let's look at the mistake bound theorem. This mistake bound theorem is attributed to two people, Novikov and Bloch. I think they were on different sides of the Iron Curtain at that time. So let's set things up. So imagine that you have a sequence of training examples, x1 paired with the label y1, x2 paired with the label y2, and so on. And each example is some n-dimensional vector with, and each label can either be -1 or 1. And I'm stating one other piece of information that each xi is less than some number r, or the length of xi is less than some number r. This is not a real constraint. We can always find such an r because you have these points that are, each xi is just a point in a high dimensional space. So you have points in high dimensional spaces. And let's say this is the origin here. Let's say I find the farthest point from the origin, and I'm calling this distance r. That means the distance of every point, there exists some number r, such that the distance of that every point from the origin is less than that number r. What I'm really doing is I'm finding the farthest point from the origin and drawing a giant circle around the thing that contains all the data points. I can always draw a large circle that contains all the data. Circle in 2 dimensions, a sphere in 3 dimensions, a hypersphere in n dimensions. But in any case, I can draw a giant circle that contains all the data. R is simply the radius of that circle. This is not really a restriction. It's just assigning a name to that radius. It's saying all points lie inside a giant circle of radius r. So we can always find such an r. So we have a sequence of examples such that every point lies within a giant circle of radius r, which is really saying the points are the farthest point is at a distance of r. Now, the next condition, so far we've introduced no conditions. We've not changed anything. We're just saying we have some data. Now let's introduce a condition. Suppose there's a unit vector. I'm going to call that u. U is a unit vector. That means it has the norm of u is 1, such that for any example xi, yi, we have y times u transpose x is greater than gamma. Gamma is a positive number. This is a very complicated way of saying that there exists a weight vector u such that y u transpose x is positive. What does it mean to say that y u transpose x is positive for that one example? What, sorry?
There is no mistake, that is why.
There is what?
No mistake.
There is no mistake on that example. If y u transpose x is positive, that means the sign of y plus or minus 1 and the sign of u transpose x are the same. That means that the weight vector, if u was a weight vector, then u correctly assigns a label for that particular example. Remember, we saw before that yw transpose x being negative means mistake. Yw transpose x being positive means no mistake. In fact, not only am I saying it's greater than 0, I'm saying it's greater than gamma. Gamma is the margin of the data. You're saying what this says is the margin of the data, the point x comma y is at a distance at least gamma, sorry, the point x is at a distance at least gamma away from the hyperplane u on the correct side. For positive examples will be on one side, negative examples will be on the other side. And this is importantly true for every single example. So for every single example, yi u transpose xi is greater than gamma. That means every single example will be correctly classified by this vector u, and it will be put at a distance at least gamma away from u. This is another way of saying the data has a margin gamma. The data not, but remember, it's not just the data has a margin gamma. The data is linearly separable, and gamma decides how difficult the data set is. If gamma is very small, the pluses and the minuses can be very, very close to u. If gamma is large, plus there's a big gap between the pluses and the minuses. Like the picture that I showed you before. What this says is there's some weight vector u that perfectly classifies the data, and the margin is at least gamma. Then the perceptron mistake bound theorem says the perceptron algorithm, we're talking about the original perceptron that operates on the stream of examples, will make no more than r square over gamma square mistakes on the training data. Let's look at this number a little bit more carefully. R square over gamma square. Gamma is in the denominator. Remember, if gamma is large, the margin is large, the learning problem is easier. If gamma is large, then this quantity becomes small. The number of mistakes that are being made by the perceptron algorithm becomes small if the learning problem is easier. With an easier data set, the perceptron algorithm makes fewer number of mistakes. If gamma is really small, then the perceptron algorithm can make more mistakes because it's something divided by gamma square. R is simply a normalizing factor. R is just saying, I've seen versions of this exact theorem that says that all the points lie inside a unit ball. It's just to kind of remove the fact that you can essentially zoom into the data to make it look like the margin is bigger. R normalizes that part out. But ignore the fact that R is there for now. The important point here is the number of mistakes is inversely proportional to gamma square. Smaller margins means more mistakes. That's one important observation. The second important observation is that the number of mistakes is actually finite. The perceptron algorithm will make no more than these many mistakes, which is just a crazy observation. It just says, if your data set is linearly separable, after making r square over gamma square mistakes, your perceptron algorithm will never make any more mistakes in the future. If you knew that your concept was some linearly separable concept and you could measure gamma, then you can actually count, you can actually predict the number of mistakes your perceptron algorithm will make, the maximum number of mistakes. And after those many mistakes, it doesn't matter what your initial weights are. After making those many mistakes, you are guaranteed your perceptron will never make any more mistakes. That's a very strong claim. You are guaranteed to have quote unquote finished learning. You have learned the concept. Your perceptron has learned the concept. Because there are never going to be any mistakes on any future examples. It doesn't matter. Remember, I talked about this adversary, right? The adversary is lining up the examples so that this thing fails. Even if an adversary picks examples that makes the learning process as hard as possible, after making r square over gamma square mistakes, the adversary loses. Questions? Yes.
This is only about for the standards, so we're not running.
Yes. Yes, this is for not the standard. This is like the online perceptron. This is for the online version of the perceptron, the one that was invented in the 1950s, because the theorem is from the 1960s. Yes.
So does this mistake bound theorem also apply to the variants that we covered today? Like
Not quite. No, it doesn't. The variants are have other properties. The standard perceptron algorithm that we saw, technically speaking, if you fix the learning rate for the algorithm, this mistake bound still applies. So the standard perceptron that I showed you, where the learning rate R was fixed and it did not ever change, this mistake bound still applies. But if you start changing the learning rate, then the guarantee no longer holds. Other guarantees kick in, it turns out. Yes.
How many like training examples do we need for it to like guarantee this for like?
Oh, that's a good question. The question was, how many examples do we actually need to see before these many mistakes happen? The theorem says nothing about that. That's a good sort of a loophole that you caught. It's almost like you're a lawyer. Because let's say that somehow let's say that I calculated r square over gamma square, and I find that the answer is 3. R square over gamma square is 3, suppose. That means this algorithm will make 3 mistakes in its life and never again, ever. That's all you know. You do not know when those mistakes will happen. So maybe the first mistake happens after the first example, the second mistake happens after the 10th example, and the third mistake happens after the 100 billionth example. You do not know. The theorem does not say anything about that. However, I want you to reflect upon the following. If the third mistake happens after 100 billion examples, that means your perceptron is fairly good. It survives 100 billion examples without making a mistake. So in the online setting, it's good enough. So in the online setting, this is a reasonable idea. But if you're thinking of it as in this batch setting where you have to iterate over the data set, then you need to start worrying. Just yes.
I guess doesn't it also depend on the learning rate? If our learning rate is very, very small, wouldn't we expect to make more mistakes and take longer?
Yeah, for proving this particular thing, I'm assuming that the learning rate is 1. If it turns out that the learning rate is not 1, you will get another thing that shows up in the denominator. The learning rate features in the denominator. Another thing that also features here is this. I assume that this u is a unit vector, right? If u were not a unit vector, then it's going to show up in the numerator. So the full mistake bound would be u square r square, the norm of u square r square divided by, I think, the learning rate square times gamma square. No, the learning rate times gamma square. So learning rate features in the denominator. For the version that I'm writing here, you're assuming that the learning rate is 1. There's a lot of symbols here, but if you kind of pull out the math and just think about what this means, what the theorem says is, suppose you have a binary classification data set in n features. If the data set is linearly separable, then the perceptron algorithm will succeed in finding a separator, a perfect separator, after only a finite number of mistakes. That's the crux of this theorem here. Normally, what I would do in this lecture is actually prove this mistake bound for you. But then I want to try something different this year. I want to make you prove it on your own. So it's part of your homework. Actually, it's not exactly part of your homework. The proof's in the slides. I'm going to skip through it very quickly. The proof's in your slides. It's a very simple proof. Trust me, it's a very simple proof. It's if you write it down, it's about this big. It's like, less than half a page. So what I'm going to ask you to do is go through the proof on your own time, because in your homework, we've asked you to prove the perceptron mistake bound for a variant of the algorithm. And we'll walk you through the steps. It forces you to understand the proof. I'm starting to believe that the best way to learn math is not to watch someone do it on a slide, but to do it yourself. So I would rather have you work through the proof on your own rather than you just listen to me talk about the proof. So for your homework, what you'll do is actually see the proof that's on the slide. You can access it. And try to map it to the variant, because the variant is also going to have a similarly structured proof. But the intuition for the proof is that, I don't want to talk about the intuition, because what will happen is then I'll start talking about the entire proof. Work it out, because it's kind of a very neat proof. So just check it out. Okay. But we have this theorem here. Questions? If there are no questions, let me make you think about this a little bit more. I talked about this R and gamma here, right? There's R and gamma. Gamma is the margin of a data set. Do you know the margin of a data set? If I give you a new data set? Because in order to know the margin of the data set, you need to know this U. If you knew the U, what's there to learn? You already have a separator. So the margin of the data set depends on this oracle or this hidden function U, which we don't have access to. So this is a theoretical concept which we actually cannot employ directly, because if you knew that a data set is the best way to show that a data set is linearly separable is to actually produce a linear classifier that separates it. If you can produce a linear classifier that separates it, then you can calculate the margins. If you have produced a linear classifier to calculate the margins, you don't need to run Perceptron because you already have the linear classifier. You don't care about how many mistakes it makes, right? So the margin is a bit of a theoretical concept. However, a cool way of showing that a data set is linearly separable is to run the perceptron algorithm. If you have a collection of points and you want to check whether they are linearly separable or not, you can just run perceptron on it, and if perceptron converges, it's linearly separable because of this theorem. If not, it's not linearly separable because of this theorem. And that's exactly how the perceptron algorithm was actually invented before Frank Rosenblatt wrote his famous paper in the 1950s, early 50s. There were two papers that invented the perceptron algorithm without calling it perceptron, without calling it learning or psychology or brain or anything. It was presented as mechanical ways of determining whether a set of points, two sets of points, overlap or not. Because if they don't overlap, that means they are linearly separable. If they are linearly separable, this procedure will converge. But we can calculate R and gamma for toy data sets. For Boolean functions, for instance, R is the property of the dimensionality. So for instance, if you have Boolean functions in n dimensions, it turns out R square is exactly equal to n. I'll show you the example in 2 dimensions. If you have Boolean function in 2 dimensions, I have 2 dimensions. Let's say this is the point 0, 0. This is the point 1, 0. Right? Now, what is R? R is simply the distance of the farthest point from the origin. It's the radius of the circle that contains all the data. So I can draw this giant circle that oh man. that contains all the data. You can imagine that circle that goes around this thing. So the radius of that is this distance here. What's the distance of 0, 0 to 1, 1? This is not a trick question. It's not 1. So I have the square. I'm asking about the length of the diagonal of the square. Square root of 2. So r is square root of 2. That means r square is 2. I have 2 dimensions and r square is 2. If you have n dimensions, it turns out r square will be equal to n. R is really very closely tied to the dimensionality of the data. It doesn't have anything to do with the separation of the pluses and the minuses. Because R does not account for whether the example has a label plus or a minus, it's just about the dimensionality of the data. On the other hand, gamma is a property of the data that we've already seen that. Gamma is a property of the data in that data sets that have the pluses and the minuses very close to each other will have a smaller gamma. If the pluses and the minuses are farther away from each other, you have a larger gamma. So in this example that we have, I'll just show you the example. And if you have, let's say, the point 1, 1 has a label plus and everything else has a label minus, what function is this, by the way? If let's call this feature x1 and this is x2, the label is of a point is plus if both x1 and x2 are and. It's and. You can say it. You don't have to mime it. It's the and function. And the margin of this data is simply, imagine that there's a hyperplane that goes through this. It's the distance of this point from here to here. This is a property of the data. Okay, so some sort of I want to present a set of sort of puzzles to kind of help you appreciate this a bit more. You can ask if you have, if your function is a Boolean disjunction. I showed you conjunction. If your function is a Boolean disjunction, you can ask how many mistakes will the perceptron make. You can to answer that question, you need to calculate r and gamma and just apply that. So if you want to play with that question a little bit more in detail, I'll start with 2 dimensions. In 2 dimensions, I've already shown you that r equals 2. R square is 2. Calculate gamma, and you can ask what's r square over gamma square, and generalize that to n dimensions. We've already seen k disjunctions, where your disjunction has only no more than k variables in it. You can ask what's the number of mistakes the perceptron algorithm will make on a k disjunction. Once again, you calculate r and gamma. The third question is actually a little bit more difficult. If you have a k disjunction, can you invent a sequence? Can you invent a sequence of examples that will force the algorithm to make order of n mistakes in n dimensions? That's a little trickier. I'll leave it for you as an exercise. It forces you to think about how points are arranged in the high dimensional spaces and forces you to kind of get a small headache thinking about hypercubes. I'll leave these questions as exercises. We can discuss these in office hours if you want. So let's start wrapping this up. The perceptron algorithm makes no assumption about the distribution of the data. You could have an adversary that forces the algorithm to make r square over gamma square mistakes, but the good news is after those many mistakes, the adversary always loses. After making those many mistakes, we can be guaranteed that our learning is done. We don't need to see any more data. Even without seeing any more data, we can give a certificate that we have learned the concept. Of course, to actually give that certificate, you need to know gamma, for which you need to know the concept to begin with, but that's a technicality that's not really theoretical, that's only a practical issue. I say only a practical issue, it's a practical issue. But speaking of practical issues, there's another one. This only applies to separable data sets. The real world is not linearly separable, which means we can never really expect never to make mistakes again in the future, at which point we have to think about other approaches we can at best hope for high accuracy rather than perfect accuracy. And if you want to increase the accuracy, you have to get more data or do other sorts of learning tricks. One of the important learning tricks that you've seen today is the idea of averaging. Averaging can improve generalization. So what you need to do, what you need to learn or know from this particular part of the lecture is what the perceptron mistake bound is, also what the margin is to understand what the mistake bound is. And you need to be able to prove this mistake bound as you will do in your homework. But to kind of step things up a little bit more, this brings our unit on perceptron to an end. We've seen the perceptron is an online learning algorithm. While the original algorithm is not really widely used, you can see the bones of that algorithm even in modern machine learning implementations, where there's this idea of you have an example, you do something with it, and you update the weights. That keeps showing up all the time. In particular, this uses an additive update to the weight. That means you have W is W plus RYX. You're adding. There's another family of online algorithms which we are not going to cover this semester, where the updates are multiplicative, and that family has very, very cool sorts of bounds. And if you're interested, you can ask me and I'll tell you about it, or I'll tell you about it right now. There's an algorithm called the Winnow algorithm, which comes with very, very neat properties. In practice, we don't use this at all because our hardware, turns out, can perform this operation far more efficiently, and GPUs are much better suited for doing those things. So we end up using additive updates all over the place. The perceptron algorithm has a cool geometric intuition, which you must you must know. It comes with a mistake bound. We've just seen the mistake bound, and you should know what the theorem is. And there are many practical variants for the perceptron algorithm. You should be able to implement them. You should be able to implement the perceptron original algorithm, its variants, averaging, and so on, and also prove the mistake bound theorem. And everything there, your homework forces you to do. So at this point, you should be able to start doing your homework. Hopefully, it's already posted on Canvas. It's on Canvas, and you have 2 weeks for that. Okay, we have a minute left. I do not want to start a new unit, so I'll give you a minute of your life back.